Catching events. Okay, so we have set up our contract to emit events. How do we see the results of a transaction and catch the events? The web3.js library provides a data structure that contains a transaction's logs. Within those, we can see the events generated by the transaction. Let's use Trouble to run a test transaction on the revised faucet contract. Follow the instruction in the Trouble section to set up a project directory and compile the faucet code. The source code can be found in the book's GitHub repository under code/trouble/faucet events. Inside the console, run the following command. 1. Trouble develop. 2. Compile. 3. Migrate. 4. Faucet.deploy with a callback that stores the result in a variable called faucet.deploy. 5. Faucet.deploy.send 1 ether and a callback that takes the result and logs out the result.logs zeroth events and the result.logs zeroth args. The output is deposit from 0x627 ... amount big number S1 E18 C 10,000 in an array. Final command faucet deploy.withdraw of 0.1 ether with a callback that prints out the result.logs 0 event and the result.logs 0th args. The output is withdraw to 0x627 ... amount big number S1 E17 C 1000 in an array. After deploying the contract using the deployed function, we execute 2 transactions. The first transaction is a deposit, which emits a deposit event in the transaction logs. Next, we use the withdraw function to make a withdrawal. This emits a withdrawal event. To get these events, we look at the logs array returned as a result of the transactions. The first log entry contains an event name in log 0th event and the event arguments in log 0th args. By showing these on the console, we can see the emitted event name and the event arguments. Events are a very useful mechanism, not only for intra-contract communication, but also for debugging during development. Calling other contracts, send, call code, delegate call. Calling other contracts from within your contract is a very useful but potentially dangerous operation. We will examine the various ways you can achieve this and evaluate the risks of each method. In short, the risks arise from the fact that you may not know much about a contract you're calling into or that is calling into your contract. When writing smart contracts, you must keep in mind that while you may mostly expect to be dealing with EOAs, there is nothing to stop arbitrarily complex and perhaps malign contracts from calling into and being called by your code. Creating a new instance. The safest way to call another contract is if you create that other contract yourself. That way, you are certain of its interfaces and behavior. To do this, you can simply instantiate it using the keyword new, as in other object-oriented languages. In Solidity, the keyword new will create the contract on the blockchain and return an object that you can use to reference it. Let's say you want to create and call a faucet contract from within another contract called token. Contract token is mortal, open brace, faucet, underscore faucet. Constructor with no arguments, open brace, underscore faucet equals new faucets with no arguments. Close brace, close brace. This mechanism for contract construction ensures that you know the exact type of the contract and its interface. The contract faucet must be defined within the scope of token, which you can do with an import statement if the definition is in another file. Import faucet.sol. You can optionally specify the value of ether transfer on creation and pass arguments to the new contract's constructor. Underscore faucet equals new faucet dot value of 0.5 ether, called with no argument. You can also then call the faucet functions. In this example, we call the destroy function of faucets from within the destroy function of token. Function destroy, owner only, open brace, underscore faucet.destroy with no argument, close brace. Note that while you are the owner of the token contract, the token contract itself owns the new faucet contract, so only the token contract can destroy it. Addressing an existing instance. Another way you can call a contract is by casting the address of an existing instance of the contract. With this method, you apply a known interface to an existing instance. It is therefore critically important that you know for sure that the instance you are addressing is in fact of the type you assume. Let's look at an example. Import faucet.sol. Contract token is mortal. Open brace. Faucet underscore faucet. Constructor with one parameter. Address underscore f. Open brace. Underscore faucet equals faucet of underscore f. Underscore faucet dot withdraw of 0.1 ether. Close brace. Close brace. Here, we take an address provided as an argument to the constructor underscore f, and we cast it to a faucet object. This is much riskier than the previous mechanism, because we don't know for sure whether that address actually is a faucet object. When we call withdraw, we are assuming that it accepts the same arguments and executes the same code as our faucet declaration, but we can't be sure. For all we know, the withdraw function at this address could execute something completely different from what we expect, even if it is named the same. Using addresses passed as input and casting them into specific objects is therefore much more dangerous than creating the contract yourself. Raw call, delegate call. Solidity offers some even more low-level functions for calling other contracts. These correspond directly to EVM opcodes of the same name, and allow us to construct a contract-to-contract call manually. As such, they represent the most flexible and the most dangerous mechanisms for calling other contracts. Here's the same example, using a call method. Contract token is mortal. Open brace. Constructor with one parameter. Address underscore faucet. Open brace underscore faucet dot call with two arguments, withdraw and 0.1 ether. Close brace, close brace. As you can see, this type of call is a blind call into a function, very much like constructing a raw transaction, only from within a contract's context. It can expose your contract to a number of security risks, most importantly, reentrancy, which we will discuss in more detail in the reentrancy security section. The call function will return false if there is a problem, so you can evaluate the return value for error handling. For example, if negation of underscore faucet.call with two arguments, withdraw and 0.1 ether, open brace, reverts with one argument, withdrawal from faucets failed, close brace. Another variant of call is delegate call, which replaced the more dangerous call code. The call code method will be deprecated soon, so it should not be used. As mentioned in the address object section, a delegate call is different from a call in that the message context does not change. For example, whereas a call changes the value of message.sender to be the calling contract, a delegate call keeps the same message.sender as in the calling contract. Essentially, delegate call runs the code of another contract inside the context of the execution of the current contract. It is most often used to invoke code from a library. It also allows you to draw on the pattern of using library functions stored elsewhere, but have that code work with the storage data of your contract. The delegate call should be used with great caution. It can have some unexpected effects, especially if the contract you call was not designed as a library. Let's use an example contract to demonstrate the various call semantics used by call and delegate call for calling libraries and contracts. In callExamples.sol, an example of different call semantics, We use an event to log the details of each call and see how the calling context changes depending on the call type. As you can see in this example, our main contract is caller, which calls a library named called library, and a contract named called contract. Both the called library and the contract have identical functions named called function, which emit an event named called event. The event called event logs three pieces of data: message.sender, transaction.origin, and this. Each time called function is called, it may have a different execution context with different values for potentially all the context variables, depending on whether it is called directly or through delegate call. In caller, we first call the contract and library directly by invoking called function in each. Then we explicitly use the low-level functions call and delegates call to call called contract.called function. This way, we can see how the various calling mechanisms behave. Let's run this in a truffle development environment and capture the events to see how it looks. 1. Migrate. 2. Caller.deployed with no arguments, and a callback function that sets the results to caller deployed. 3. Caller deploy.make calls of called contract.address, and a callback that iterates over the results logs and log out the arguments. Let's see what happened here. We call the make calls function and pass the address of called contract, then caught the 4 events emitted by each of the different calls. Let's look at the make calls function and walk through each step. The first call is call contract.call function with no argument. Here, we are calling called contract.call function directly, using the high-level ABI for call function. The event emitted is sender 0x8f ... origin 0x62 ... from 0x345 ... As you can see, message.sender is the address of the caller contract. The transaction.origin is the address of our account that sends the transaction to caller. The event was emitted by called contract, as we can see from the last argument of the event. The next call in make calls is to the library, called library.call function. It looks identical to how we call the contract, but behaves very differently. Let's look at the second event emitted. Sender 0x62 ... origin 0x62 ... from 0x8f ... This time, the message.sender is not the address of caller. Instead, it is the address of our account, and is the same as the transaction origin. That's because when you call a library, the call is always delegate's call and runs within the context of the caller. So, when the called library code was running, it inherited the execution context of caller, as if its code was running inside caller. The variable this, shown as from in the event emitted, is the address of caller, even though it is accessed from within called library. The next 2 calls, using the low-level call and delegates call, verify our expectations, emitting events that mirror what we just saw.